solve one problem on unidirectional steady-state conduction heat flow for a infinitely long hollow cylinder without internal heat generation. We will first read what is the given question. A thick-walled copper cylinder has an inside diameter 1 cm and outside diameter 2 cm. The inner and outer surfaces are held at 290 degrees Celsius and 310 degrees Celsius respectively. Assume K varies with temperature as K is equal to 371.9 in bracket 1 minus 9.25 into 10 raised to minus 5 in bracket T minus 150. Determine the heat loss per unit length. Also find the radius at which temperature is 300 degrees Celsius. If we observe the given question, this is the case of infinitely long hollow cylinder. That means length of cylinder is infinite. So we will consider heat flow is taking place only along thickness. We will first draw the diagram as per given data. Inner radius R1 is given 1 cm and outer radius R2 is given 2 cm. So we will draw here, this is the inside radius which is R1 and this is the outside radius that is R2. Then the temperature T1 is also given 290 degrees Celsius and temperature T2 is 310 degrees Celsius. Now we will first solve the first question, that is the heat loss per unit length, and for that we will apply the Fourier's equation. Now why we are considering here the Fourier's equation? Because in this case steady state conduction process is taking place. Second one, heat flow is unidirectional. Now for this question we will consider here the heat flow is taking place in the direction of x, and I will show here the direction of x, that is towards the right hand side direction. And there is no any internal heat generation. Suppose all these conditions are satisfied, then we have to apply the Fourier's equation for the conduction process. So what is the Fourier's equation for infinitely long hollow cylinder? So this Fourier's equation is Q by A is equal to minus K dt by dr. Now as per given data, K is also defined in terms of T. If we observe this diagram, here variables are radius R and temperature T. So these are the two variables, and here K, that is the thermal conductivity, is defined in terms of variable T. That means we can say that K is the function of T. So it is 371.9 in the bracket 1 minus 9.25 into 10 raised to minus 5 and in this bracket T minus 150. So we have to simplify this. So how to simplify? We have to multiply here 9.25 into 10 raised to 5 with this inside bracket, and then again we have to solve this bracket by multiplying with 371.9. So when we simplify, it is 377.06 minus 0.0344 T. So we can take here, this is the K. Now we will observe here this Q, that is heat flow. So this Q is not the function of R, or we can say that Q is not the function of R. That means it is constant. So we have to take this outside of integration. Then what about area? So area for this infinitely long hollow cylinder, so if we observe here this area, that means we have to take for hollow cylinder 2πRL. That is, A is the function of R and R is variable. So we have to transfer this dr to the left hand side. Then this K is the function of T, because K here defined in terms of T. So K is the function of T. So we have to take here as a K dt. So how we simplify this? So Q by A dr is equal to minus K dt. Now we will apply the boundary conditions. So when we have to take the integration, we have to take the integration that is limited to this inner radius and outer radius. So this is limited to this only this thickness material, because heat flow taking place only along the thickness. So when R is equal to R1, then T is equal to T1, and when R is equal to R2, then T is equal to T2. Now we will apply these boundary conditions to this equation. So for that we will take the integration on both sides. So when we take the integration on both sides, then Q is not the function of variable, that is R. So we have to take Q outside. Then here A is equal to 2 pi RL. So 2 pi L is also constant. So we have to take this 2 pi L outside the integration. So how we can write here? That is Q integration of R1 to R2 dr by 2 pi RL, which is equal to minus, instead of K we will write this, that is integration of T1 to T2. Instead of K we will write this simplified form and dt. Now Q divided by 2 pi L. Now what is the integration of dr by R? That is it is in the form of 1 upon x. So 1 upon x, what is the integration of 1 upon x? That is ln x. So we will take here ln R and we will give the limits R1 to R2. Now here if we observe, there are two terms, that is 377.06 dt. So what is the integration? That is 377.06 t minus 0.0344 t dt. So t dt, what is the integration of t dt? That is t square by 2. So we have to write here t square by 2. Now outside the bracket we have to give the limits t1 to t2, but here is the minus sign and we have to remove this minus sign. So we will give here, that is lower limit is t1 and upper limit is t2, but here if we have to remove this minus sign, then we will give lower limit t2 and upper limit t1, that is t2 to t1. Now we know that how to simplify this. So here heat loss per unit length, that we have to find out. So we will take here QbyL is equal to, we will transfer 2 by to the right hand side. Now this ln R and limit is R2 by R2 and R1. So how to solve this? So we know that it is ln R2 minus ln R1, that is upper limit minus lower limit. So how we can again simplify this? That is ln R2 by R1. So this is in the numerator, so we have to transfer this in the denominator. That is, we are going to transfer this function or this term to the right hand side, and 2 pi also right hand side. So this is in the denominator, so it will come in the numerator. Now what about this 377.06 t? So instead of t we have to write upper limit minus lower limit, that is 377.06 in the bracket t1 minus t2. Now here also in the same way minus 0.0344 t square by 2. So instead of t we have to take upper limit minus lower limit, that is t1 square minus t2 square, and denominator is same, that is 2. So here this is the form. Now if we observe, in this case we have to put all the values. So t1 and t2 is known, that is 290 and 310 degrees Celsius. Now what about R1 and R2? So here R1 is 1 centimeter, so standard unit is meter, 0.01 meter. And here 2 centimeter, that is 0.02 meter. So we will put all the values and we will calculate here the value of Qby L. When we calculate, then we will get the Qby L is equal to minus 66492.43 watt per meter. Now what this negative sign indicates? So this negative sign indicates that heat flow will take place in radially inward direction. Because if we observe, we have considered the flow is in the direction of x, that is in the radially outward direction, but because of this negative sign, flow will take place in this radially inward direction. Now we will move for the second question. So what is the second question? We have to find out radius r when temperature T is equal to 300 degrees Celsius. So for that we have formula, that is Q. So Q is equal to 2 pi Lk T1 minus T2 divided by Ln R2 by R1. Now we have here the formula for Q by L. So we will transfer this L to the left hand side. So we will get Q by L is equal to 2 pi K T1 minus T2 divided by Ln R2 by R1. Now we have to find out R when temperature T is given. So for that we will construct here one diagram, that is we will take any random radius R in between this, and what is, when here is radius R, then what is the temperature at this point, that is TR. And this TR is equal to 300 degrees Celsius, and we have to find out this radius R. So how to find out this? So we will replace this suffix 2, that is this T2 and R2. So instead of this T2 and this R2, we will put here R and TR. So I will write here as a capital R. So when R is equal to capital R, then T is equal to TR as per the diagram. Then we will replace T2 is equal to TR and R2 is equal to capital R. And as per the question, when TR is equal to 300 degrees Celsius, we have to find out this value of R. Now when we put here, that is we will get Q by L. So again I will replace here Q by L is equal to 2 pi K T1 minus TR divided by Ln capital R by R1. Now it is easy for us to solve this. Now K is given in terms of T, that is K thermal conductivity is the function of T. So when T is equal to 300 degrees Celsius, then what is the value of K? So K is equal to 377.06 minus 0.0344 multiplied by 300. So we have to solve this, then we will get the answer of K. So instead of T here we will put 300. Then we will put all the values, that is 2 pi. Then for K we will solve this bracket. Then T1 minus TR. So T1 is 290 and minus TR, that is 300. Divided by Ln R by R1. So capital R and R1 is 0.01. Now we will solve this. So when we solve this, there is only one unknown term, that is Ln R. So first we will solve this numerator. So when we solve this numerator, because 290 minus 300, we will get here negative sign, minus 2304295 divided by Ln R by 0.01 as it is, and left hand side for this QbyL as it is. Now how we will simplify this Ln R by 0.01? We can write here Ln R minus Ln 0.01. Now here this is unknown term and we can solve this. So we will take this term to the left hand side and we will transfer this term to the right hand side, that is it will move to the denominator. So when we solve this, then we will get minus 0.34655, and for the left hand side we will calculate here Ln 0.01, that is 4.605. but here this minus Ln will become plus, but what is the answer of this Ln 0.01? So when we calculate this in calculator, then we will get the answer in minus 4.605. So here are two minus signs. So when we solve this, we will get minus 4.95. And when we take inverse of Ln, then we will get the R, because on the both side here is Ln R is equal to. Here is also Ln R, because we have to transfer this term to the right hand side. So here is also Ln R. So when we take inverse of Ln on both sides, then we will get capital R is equal to 7.07 into 10 raised to minus 3 meter. So this is the answer of second question.